Hi. So the goal of this video is to talk about how sampling can impact the measurement that we're trying to make. So let's talk about a continuous signal. I have some voltage signal, maybe it's a function of time, and I am going to take snapshots of it when I sample, and I will sample at a certain frequency. And ideally, when I do this, I will get enough points so that I can determine the shape of this waveform, but more importantly, the frequency of the waveform. Because the thing in blue we don't actually measure in its entirety, we're taking snapshots of it to give us this thing in red. And looking at this, it seems that we can get a good idea of what we're trying to measure. But depending on how fast we sample or how slow we sample, we may end up interpreting our data incorrectly. So the goal of sampling is to have a high enough sampling frequency to ensure all frequencies are being captured correctly. And what I mean by that is, in this example that I had with the blue sine wave, let's say that this is a sine wave that occurs over maybe 1 second. That's the period. I am sampling pretty quickly in order to get all these data points. Now imagine that I give you the same exact sine wave, and instead of sampling quickly, I sample more slowly. So instead of getting a lot of data points that produce the sine wave, I end up with maybe a data point here, a data point here, and maybe a data point here. We'll ignore my scaling. We'll assume it's not to scale. And maybe this looks like to us something like this, because we don't really necessarily know what's going on in between them. And the frequency of what that new signal is may be different than the original signal. Because at the end of the day, the goal is, if I am trying to measure something in an experiment, I want to know what frequencies are present in that situation. So if I have some sort of machinery that's vibrating and I hook up an accelerometer to it in order to determine what frequency it's vibrating at, if I'm not sampling quickly enough, you may end up believing that there is a frequency present that actually doesn't exist. And that is the idea of aliasing. So aliasing, I don't want to make sure I kind of follow the definition I gave in my notes, basically says that if we sample at too low of a frequency, we may end up presenting an incorrect frequency. What I'm going to do is I'm going to stop sharing this screen. I'd rather share my lap or my computer for a second. Let me share the screen here.
So if you look at a signal that is, let's say 120 hertz, which is this black one, that black one will have 120 periods in 1 second. We can see we have a lot of periods here in this 0.08 second span. And I want to sample it fast enough to be able to see and recreate that signal. Now, if I'm sampling too slowly, which in this situation I'm sampling at 50 hertz, which is a little too slow, I will sample every 0.02 seconds. That's the reciprocal of 50. So if you look, I collect my first data point, that's these blue points here at 0, 0.00 or 0.02, 0.04, 0.06, and 0.08. That's our sampling frequency of 50. Now, if I try to connect the dots using what's known as a cardinal series to reconstruct the signal, I will see a sine wave that is at a much lower frequency compared to the signal I actually want to measure. If we look at the period of the red one, if I follow this out, we see that a period finishes at around 0.05 seconds, while a period for the black one is less than 0.01 seconds. Very different periods, very different frequencies, because we are not sampling fast enough. So this black signal ends up being aliased to become this red signal.
So how do we present aliasing? First off, let's look at the idea of Nyquist, the Nyquist-Shannon sampling theorem. Which says that we need to sample at least twice the maximum frequency present in our signal. So I'm going to say that my sampling frequency, Fs, this has to be greater than or equal to twice the max frequency that's in our signal. So if I have a signal that's composed of one wave like this, and then another wave that looks like this frequency is higher than this one. I need to ensure that I'm sampling at least twice as fast compared to the frequency of the highest signal present. Because otherwise, this signal may represent itself, and maybe it looks like that because of the fact that I am sampling at very strange times. Because I'm not sampling quickly enough. So basically doing this is what we say ensures spectral fidelity. Meaning that if I were to do, let's say, a Fourier type of transform on it, we would see that we have a frequency, let's say that this blue one is frequency, I don't know, F1, and this red one is frequency F2. I might have some peak at F1, and I'll have some peak at F2, assuming we're sampling fast enough. We meet Nyquist. But let's say that we don't meet Nyquist. Here's F1. Let's say we're sampling fast enough for this. But then the one that should have been located at F1 doesn't actually exist anymore because we're not sampling fast enough. We may think it's here at some other frequency because of this aliasing problem. And we don't want this. We want to match the physical situation. So the question is, how do we determine what our aliased frequencies are? So what is the aliased frequency? And I'll also call this maybe the apparent frequency for a signal sampled too slowly. And that's where the idea of folding diagrams comes in. So a folding diagram is one that is used to predict or to tell us how a signal will present itself if we're aliasing. And before we go into what this looks like, I want to define a couple things. First off, the Nyquist frequency that I'll call Fn, this is defined as the sampling frequency over 2. Oops. So this is sampling frequency over 2. We will use this to determine if we are aliasing essentially any frequencies above Nyquist, the Nyquist frequency, will be aliased. So if I know what my sampling frequency is, I can determine what frequencies I can accurately measure. Any frequencies above that will end up presenting themselves differently, which is a problem. I'm going to define a few more variables here. I'm going to say that F true, this is the actual frequency of the real world, the analog signal, etc. And F apparent is exactly what I was talking about here. Basically, how that frequency presents itself to us on the computer or from our perspective. So this is essentially the digital signal's frequency determined by, first off, what the true frequency is and also how fast we're sampling by F true and Fs. And the reason why these two variables are important, or these three concepts, is because we will use them in what's called a folding diagram. So a folding diagram, the way that it works is that if I draw a picture or a graph, I'm going to say that this x-axis is going to be the ratio of F true to the Nyquist frequency. And we're going to do an example to illustrate this. But if I have some true frequency, let's say it's 50, and my Nyquist frequency is 10, I can take the ratio and get a number. And that number will be plotted here. And I'll typically do this in increments of 1. These numbers don't really change. And what I'm going to do is I'm going to draw triangles. And the first triangle I'm going to draw is this perfectly straight line, or perfectly, I'm going to say it's a line with a slope of 1, which means that on this axis, this will also be a 1 at the point that they touch. And before I keep going with the triangles, I want to make sure that we understand this, that if this point is at, let's say, 0.3, this one, the y value will also be 0.3 because this line is basically the same as y is equal to x. It's a one-to-one relationship. So anything that falls on there will have the same x value as they do the same y value. I just want to point that out now. It'll come back in a second. So I'm going to draw the other side of my triangle and have it touch. I'm trying to make them kind of symmetric. That's 2. I'm going to do this again. Try to get it to be kind of the same. I'm going to erase these for now since I'm not good at drawing. That'll be 3. And we'll do one more for 4. So depending on our f true and our fn, we will look at some x value. And maybe I'll give an example. Let's just say that fs is 30. And I'll say that f true is 20. So what we need to find our x value on this graph, I gave you f true. We now need to look for fn, and fn is simply half of the sampling frequency, which is 15 hertz. So if I take the ratio of f true over fn, this will be 15 over 20. Oh, sorry, 20 over 15, which is what? Ugly fraction. Of course it is. That's okay. Let's just say that this is 1.33. I chose bad numbers off the top of my head, but let's just roll with it. 1.33. What I will do is I will go to 1.33 on the x-axis. And what I'm going to do is I'm going to draw a line up to the line of a triangle. And once I hit that triangle, I'm going to take the point here and I'm going to reflect it over the axis where an integer is. So if I had a point, let's say here, it would reflect over to here, and then this one would reflect over to here. They just keep folding over. Like if you were to take a piece of paper and fold it, where would that point end up? And in this example, we see that this distance here is 0.33 away, which means that this distance has to be 0.33 away. So if I do 1 minus 0.33, we get 0.67. So that means that this value here is 0.67. Now, because of the fact that this line here is y equals x, that means that this point is also 0.67. And I didn't tell you what this y-axis is yet, but we found the value on that axis. It's going to be 0.67 in this example. This axis ends up being f apparent over fn. So if I were to say that f apparent over fn is equal to 0.67, what that means is that f apparent is 67% of the Nyquist frequency. So that'd be 0.67 times 15. That was the Nyquist frequency. So 0.67 times 15, that ends up being 10. And that's what we will see on our computer screen. So to summarize this conceptually, a frequency of 20 hertz, that's F true, being sampled at 30 hertz. And if you keep in mind, we're not sampling double that frequency, which basically tells us we're going to alias. We would need to sample at least 40 to not alias. But in this situation, we're not sufficient, so we're going to alias. So a frequency of 20 hertz being sampled at 30 hertz will appear as a 10 hertz signal. If you're doing your experiment, you have something maybe that's vibrating. You have this beam that's vibrating up and down. You have a little sensor on it that's going to the computer. And instead of seeing the real vibration of this, maybe the real vibration is at 20 hertz. We end up seeing something that is slower at 10 hertz because of the aliasing. That's the general idea. I want to do another example where we do multiple folds, but that's the concept. Let's do one more where I'm going to tell you that F true is 120 hertz. We're sampling at 100 hertz. And we want to know what will happen to that 120 hertz signal. So basically, what is F apparent? First, find the Nyquist frequency. That's going to be Fn. That's going to be Fs over 2, which will be 100 over 2. The Nyquist frequency is 50 hertz. So let's go ahead and draw our triangles. I'm going to do a rough sketch. I'm not going to spend as much time drawing the triangles. But I know that this first one will be at a point of 1. This is 2. This is 3, and this is 4. And this axis is going to be the true frequency over the Nyquist. This axis is the apparent frequency over the Nyquist. So first off, we ask ourselves, is this true signal being sampled at least double? And the answer is no. We're sampling at 100. So we would have to sample at least 200. Or sorry, not 200. I need to sample at least double this. I need to sample at 240 to do that. We're sampling too slowly at 100 hertz. So that means we're going to alias. So let's figure out what that's going to be. So this ratio here, F true over Fn, is going to be 120 over 50, and that is the same as 2.4. That, again, that's our x-axis value. So we're going to come over and go to 2.4. I'm going to draw a line up and go to there. This distance is 0.4. So if I were to fold that over the 2, if I were to fold that over the 2, this would also be 0.4 to the other side, which would mean that this is 1.6. Now, when we stop folding is when we reach the leftmost triangle. Because at that point, we have this line that's 1-to-1, and we can determine based on the x value that it lands on what the y value is. So I have to fold this again over the 1, but this time I see that I'm not 0.4 away anymore. I'm now 0.6 away. So I'm going to fold this over, to here, where now this distance is 0.6, which means that this y, this x value here has to be 0.4. And because of that symmetry, we know that F apparent over Fn has to be the same as 0.4. that says that F apparent is 0.4 of the Nyquist, and the Nyquist frequency was 50. F apparent for this example ends up being 40% of 50, which is 20 hertz. So this was the original signal of 120, and we end up seeing 20 hertz. So I do want to share my screen one more time. I think I clicked the wrong thing. That's better. I'm going to run this again. Let's stop this. I'm going to run this. And our frequency in this case, our true frequency was 120. I'll do a bunch of periods so we can see it. Our sampling frequency was 100. So we're not sampling at double the frequency. We're going to alias. And if I click OK, my graph, here it is. Oop, too many graphs. Sorry. Oops. Technical difficulties. One more time. 120. Sampling at 100. So the 1. Okay. So if we look, our true signal was 120. So that's the black one. And then the red one is the reconstructed signal, which should have a frequency of 20 hertz based on our math. So if I look at, let's say, one period of this, if I look at one period, let's say I go to here, that's 0. Okay. If I do one period of this red wave, that brings me to here. And that is around 0.05 seconds according to the simulation. If we do 0.05, that's the period, take the reciprocal, we get 20. So this black one was 120 hertz. We're sampling at 100. We end up seeing that represented as a 20 hertz signal. That is the idea of aliasing. Hopefully that makes sense. We want to avoid aliasing, so we'll try to sample sufficiently. Of course, if we sample too much, we may end up collecting too much data. We might have limitations on the data acquisition system that we're using that can't respond fast enough. But in general, that is our motivation. Hopefully this was helpful. If you have any questions, please let me know. Okay, thanks. Bye.